Statements, documentation, and online help. Wikipedia happens to be one of my favorite sites. They're my go-to resource when I'm looking for a quick definition. Speaking of which, the Wikipedia definition of syntax in the context of programming languages is that syntax of a programming language is the set of rules that define the combinations of symbols that are considered to be correctly structured programs in that language. Related term to syntax that you'll often see in programming literature is a term called lexical grammar. Wikipedia goes on to describe lexical grammar of a textual language, of which Python is certainly an example, that this grammar specifies how characters must be chunked into what are called tokens. And then to continue our trolley ride through vocabulary, a token is defined as a string of characters categorized according to the rules as a symbol, like an identifier, a number, a comma, etc. Well, how does all this stuff relate to our current nugget? Well, now that we've had a chance to understand the basic mechanics of Python in terms of what it is, what it's used for, how to install it, and we've done some nuggets where we actually began to use the language, I think now is a perfect time for us to kind of take a step back and look at what are Python statements exactly? What are Python objects? What are Python variables or names? We've been using these things consistently throughout the course. I intentionally inserted this nugget in this position now because rather than describe all this stuff on the front end when you don't know how to use statements or you don't know how to use variables, I think it's especially important now that we have some frame of reference. So we'll look at statements, we'll look at rules and best practices for using variables in Python, we'll understand the importance of documenting our code, we'll understand how comments and documentation strings work, and then we'll formally talk about and I'll show you how to access Python's rich and robust online help. Let's get to work. A Python statement is simply a keyword identifier that is reserved by Python. In other words, and as you see here, this is a list of the Python statements that are built into Python 3. Reserved means we're not going to be able to create a variable with any of these names. It's as simple as that. We're not going to be able to co-opt or steal any of these keyword identifiers. Now, of this 30 or so identifiers that you see, some languages have more, some languages perhaps have fewer. How many of these you'll wind up using in your daily programming? Estimated is most Python programmers would say 60 to 70%. We'll see how things go with you as you work with the language and move on in your careers. In the course of this training, I imagine we'll cover half, if not hit that 60% mark. We're looking at the most important statements that are used in day-to-day Python programming. Some of these should already look familiar. We've used def, for instance, a few times to define functions. I believe I've given some examples that include if constructs, if, elif, and else. If not, you're certainly going to get a lot of experience with if blocks in the upcoming nuggets, etc. So these are our basic Python statements that are used to construct Python programs. They're all baked into the Python interpreter, and as you know, we can import modules either from the standard library that ships with the Python distribution, CPython that is, or we can download or create our own modules and then use, you guessed it, the import Python statement to bring those in. Next, we have the backslash. We're going to be talking a lot about escape characters, and this is an overloaded character that's used for escape sequences and line continuation at the very least. Thus far, I think you've seen in our sample code that Python moves as the Python interpreter goes through your script file, line by line. And generally speaking, your statements, your expressions, etc., your declarations will all consist of one line. But that's not always the case. You may have a paragraph level string that by definition is going to run wider than your idle window or whatever your integrated development environment is. Bottom line is we can use the backslash to continue our processing on multiple lines. Makes it easier for us to see when we're coding, certainly. Another thing we need to be aware of is the distinction between the simple statement and the compound statement. In import, using import random, let's say, that's an example of a one-line simple statement. A simple statement is synonymously termed a one-line statement. These are differentiated from what are called compound statements. Compound means more than one line, or what you'd classically refer to if you're familiar with other programming languages, a block, a statement block. And this is significant, and we haven't formally talked about it yet, so listen closely. Python uses a very interesting structure for compound statements. The bottom line is Python uses what's called white space indentation in order to demarcate a compound statement or a statement block. Languages like C and its derivatives use the brace character. I'm not drawing them very well here, but you get the general idea, to delimit the start and end of a code block. Python, because it was made, as I've repeated several times thus far, is a user-friendly, intuitive language and has a strong focus on readability and legibility. Guido van Rossum in the Python community feels that white space indentation, that is to say, indenting your code using the space or potentially the tab characters, makes it much easier to read a larger script file than searching through all of those braces. Certainly, if you've done programming in C and the C family of languages, it can be, frustrating to say the least, to be debugging your code and spend a lot of your time searching open and close braces to make sure that you've correctly closed a statement block. More specifically, a compound statement in Python has two components, what's called the header line, and this could be, for instance, def when we're declaring a definition. It could be class if we're defining a class, etc. If we're doing a for loop or an if block, the first line is the header, and those are delimited by a colon. As soon as you hit enter in any IDE worth its salt, certainly idle fits this. Idle understands that you're starting a code block and will automatically give you that white space indentation, which Python best practices state should be 4 spaces. Although you technically can use the tab character to do your indents, strongly recommended you do not do that. Remember that the tab maps to an ASCII or a Unicode code point depending upon your version of Python, and you may have problems with porting your code to other operating system platforms who may interpret the tab differently, and you might wind up with jig-jags in your blocks. Much better to just use a consistent white space indentation using 4 strikes of the space key or the space bar if your IDE doesn't already do that. After your header line, you have your indentation. The rest of your block, whatever it is, a class declaration, a function, an if block, is what's called the suite. And this is simply the second part of your compound statement. Let's take a quick look at keywords, simple statements, compound statements, and line continuation before we go on. As you see, I've just created a simple list here with 3 string elements. That's an example of a simple statement. Another one would be, say, a test, maybe a membership test. Let's see if grape is in the list called L. Nope, it's not. How about apple? True, etc. As far as compound statements are concerned, we can do those directly in the interpreter, or more commonly, we can do them in a script file. We haven't introduced for loops yet, but I'm going to just give you this as an example. This statement is saying, for I, this is an arbitrary name I'm creating on the fly. I could call this anything I want to, I, J, K, whatever. And then I forgot a keyword here, in. L, of course, is our list. For is a looping mechanism that's meant to iterate through what's called an iterable. Generally, you'll use for loops with things like lists, range to give you an integer range or a numeric range, etc. And for is cool because you can step through each element in that sequence and perform some work on it. We hit colon and enter, and you'll notice we get a 4-space indentation by default. This is a compound statement. All I'm going to do in this for loop is print out the value of I, which is that name we're creating that's going to be our storage name, our storage object for each element in the L list. And I'm also going to use the len function to give us the length of each of those strings. When you're doing a compound statement in the interpreted environment, or in the interpreter I should say, what you do to run it is hit 1 space, the interpreter thinks we're going to continue this block, hit enter the second time, and then the for loop actually runs. Now let's do line continuation. Now I'll create another list. One thing that newcomers to Python might not pick up that I could help you with is that when you're doing a sequence like a list here, you do not have to, strictly speaking, throw in the line continuation character. If you want to, that's fine. We can backslash, press enter, and the interpreter keeps us in that statement. So we can then add another element, close up the list, echo the name back, and we get our object data. That's cool. But more commonly, where you're going to wind up using line continuation, in my experience, is something like a super long string. Again, a newcomer thing would be to put a space before the line continuation character. Then when we echo that name back, you notice that we have a space preserved between the first string and the second one. If we didn't want to do that, let's define a name called S2, and I'm just going to put gobbledygook here. If we wanted to do a line continuation for readability in our code, we can do backslash with no space and then continue. I'll just add Z's to make it easier to identify. And then you notice we have the full string come back just as needed. Let's talk a little bit more on this notion of white space indentation, and then we'll transition into a discussion on escape characters. According to the Python style guide, of course, all this is somewhat, not exactly tongue-in-cheek, but of course there are no enforceable rules or laws in Python, simply best practices that the community subscribes to voluntarily. That said, 4 spaces, not tabs, is generally what we use for white space indentation. And although I haven't mentioned this, in compound statements you have the 4 space between the header and the suite. You can certainly nest as many levels in your code as you want, again, maintaining a 4 space indentation. So you may have a while loop starting in the outermost container object, and then within that while loop you could be doing for loops, if, else, etc. And the net effect of this, and the idea is, and I believe in this, is that the white space indentation makes it a lot easier for us to understand the code. It's not necessarily just understanding another developer's code. Frankly, it can just as well be you making sure you understand your own code 6 months, a year in the future, going back on it. Now, where do some of these best practices come from? Not just for things like white space indentation, but also things like choosing good names, variables, etc. I'd like to introduce you to the Python Enhancement Proposal, or PEP documents. If you're familiar with the TCP/IP suite of internet protocols, you'll know that web standards in general are encoded or stored in these user-friendly request for comments documents that are put together and maintained by the Internet Engineering Task Force, or IETF. Boy, we've got a lot of TLAs, 3-letter acronyms, and FLAs, 4-letter acronyms floating around here, don't we? As it happens in the Python community, Guido et al. Guido is known as the benevolent dictator for life. This is yet another tongue-in-cheek reference to the fact that the Python community looks up to Guido as obviously a chief voice in determining how Python evolves over time. And the Python folks, in particular the Python Software Foundation, they put forth these PEP documents. Some wind up becoming features implemented in the next version of Python. In fact, a lot of them do. PEP 8 is important because it's the style guide for Python code. Let's take a quick look at it. You can just do a Google search for Python PEP 8 to find this. You'll notice that this one was in fact written by Guido himself along with a fellow named Barry Warsaw. It was created in 2001. As of this recording in April 2010, all of these suggestions for style are just as valid as they ever were. It's interesting that the document starts with Wordsworth, a quote that I've actually held onto in my life a long time before I saw it here. A foolish consistency is the hobgoblin of little minds. Interesting. And it says one of Guido's key insights is that code is read much more often than it is written. True. So as we go through this document, I'm not going to read the whole thing. I would strongly encourage you study it. Here we have right at the beginning under code layout, use 4 spaces per indentation level. For really old code, you can continue to use tabs, and then it tells us be consistent, basically. We're going to find that consistency is a huge theme, certainly with any good programming language and programming development style, but even more so in Python. Don't mix tabs and spaces. Because tabs can give us variable length indents depending upon your operating system platform, we certainly want to use spaces that are interpreted the same. Maximum line length, here we're talking about the potential of using the line continuation character or triple quoted strings, etc. So again, that's PEP 8, Style Guide for Python Code. Definitely worth your while. If you've ever heard of an Easter egg is some undocumented, I'm not going to call it a feature, but some undocumented aspect of a program that the developers normally put in for personal or internal use and is not in most cases meant to be exposed to the general public. Many times Easter eggs in video games and other programs have a humorous side. Sometimes they're pretty intense, like an old version of Microsoft Excel, I believe it was Excel 97, had a 3D flight simulator built into it. If you went to a certain cell and hit a certain keystroke, you could actually duck out of Excel and play a video game. That didn't fly well with the US government because with their rules, the C2 security rules, etc., we they certainly don't want to have their employees using a program that contains an entirely other program embedded and hidden within its code, you see? Anyway, what I'm working up to here is the fact that there are a couple Easter eggs built into Python. We can use import this. Remember, import is what we use to bring in modules from our Python path. And what this brings up is a screen dump of what's called the Zen of Python by a fellow named Tim Peters. Again, I'm not going to read this line by line, but what's especially cool about this is that just in a 20 or so lines, you read and understand this stuff and you'll get a really good feel for how Python works, or at least how it's supposed to work best practice. More humorously, at least with Python 3, you can do an import anti-gravity, and by importing the anti-gravity Easter egg module, what will happen is your default web browser will fire up and it'll go to this particular installment, 353, of the XKCD webcomic, which tends to be pretty popular among software developers and tech geeks. As you can expect, this particular comic is called Python, and it deals with the Python language. I'll leave that to you to read. Now then, what about escape characters? Escape characters are formally defined as an alternate interpretation of string data. Truly, the line continuation character that we just looked at is an example of an escape character, because instead of being interpreted by Python as a backslash or as a string literal that you might use all day long, for instance, if you want to put in, say, Windows directory paths as string literals. No, it's not given as that. When we see a line continuation character, just a backslash, this puts Python into an alternate frame of mind. That is to say, an unquoted backslash enables Python to look at the data that immediately follows it as something other than normal object data like string, etc. Now let's look at a really good example here. Let's say we create a name called txt file and we're using an open function. Don't worry about the specifics of this function yet. We're going to deal with working with files in a future nugget. But basically what this statement is doing, this name, is that it's opening a text file. At least we're trying to open a text file called text.text for writing. But at first blush, you see this code and you think, well, it doesn't seem anything the matter here, right? However, you wind up with a problem, and that is, if you know anything about escape characters, which I wouldn't expect you would at this point, \n is always interpreted by Python as a new line character, the equivalent of pressing the return or enter key on your keyboard. \t is the built-in escape character for the tab. You see what I mean? So you're going to get unexpected results for sure by running this first simple statement. So how can we correct this? There's a couple ways. I tend to favor the middle one here, where we simply escape the literal. That is to say, if we want to tell Python essentially, we do want to use the backslash as a string literal, you can simply put a \, escape character before your literal. So what your path would look like is what you see here, C:\, new, \text_. Now if you were doing a Windows Universal Naming Convention path, which as you probably know is 2 backslashes, well you're going to have to escape both of those. You see what I'm saying? A third way to do this is to use what are called raw strings, where you're essentially telling the Python interpreter everything between the quotes here, take it as a string literal. I don't care if it's an escape character or not. It's up to you on which way you consider to be more Pythonic. This is a really useful table that I've pulled from the online documentation at python.org. Certainly a table that you'll want to become familiar with. This gives us the list of string escape characters or escape codes in Python. You'll notice that to escape a backslash, we do \. We just learned that actually. To escape quotes, you can just do \single or \double. These are largely irrelevant in Python 3, of course, because I've already showed you that we can combine single quotes and double quotes all day long as we're consistent. That is to say, if we're using double quotes for the outside opening and closing of our string, we can use single quotes inside, and vice versa, but we need to be consistent. Some of the other ones that are important, really the ones that I use the most, and it's probably going to be the case with you, is the \n that translates into the ASCII line feed, or stroke of the enter key as I normally describe it in user-friendly terms, and the horizontal tab, or \t. If you're in the math science realm and you're working with non-decimal numerics, you can bring in octals and hex values by using the \o or \x as the case may be. Let's now work with escape characters a bit. Actually, I want to go back to line continuation just for a moment if I could. As you see, I'm creating a name called ls for long string, and if you want to format your string in a multi-paragraph style, for instance, I've created a Python program that's essentially a throwback to the old Infocom text adventures like Zork, etc. Great stuff if you're not familiar with that stuff. I grew up on that. But there you're putting out pretty long strings, aren't you, that are formatted pretty much as paragraphs with a blank line feed in between those paragraphs. Best way to do that in Python is to use the triple quoted string. We're going to come back to triple quoted strings momentarily in this nugget when we do doc strings, but for now just know that it works really well for multi-line strings. Remember, double quotes or single quotes, it doesn't matter. As you see, we're getting to the end of our visible area in the Python shell, so we could just keep typing, or we can use the line continuation character to be kind of strict about it. It really doesn't matter. Notice that I'm adding liberal line feeds here. I hit enter twice, and then without adding any additional quote marks, and you can just keep going. With line continuation, without, it really doesn't matter. Bottom line is, once you're finished, end the triple quoted string, and then you're good. So if we echo that back in the interpreter, you see something that might come as a surprise. The quick brown fox jumped over the lazy dog all day long, \n\n. Huh? What's that? More text and more, and then the rest is fine. This is just simply a function of working in idle. If you want to see your text in a prettier way, I would simply suggest running the print function and then passing in that string. And that's how this will look to your customer or whoever's actually running the program. Let's do some more with escape characters. It's pretty straightforward, right? How about, if we throw in a new line here, a \n, this is just interpreted by Python, just character by character, print cbt, \n, whoops, we must need a new line, and there it is, and then we continue. You might or might not get unexpected results if you think that the new line has to be like this. No, that's not the case. The new line is interpreted in your string, just like any other character is. Let's now, just for grins, do a \t, and you'll see cbt tab nuggets. Simple as that. Remember that example I gave earlier about a directory path in Windows with the / being part of that? Notice that the result here is not what we want. C:, and then we don't want a line feed, but we got one. \t is interpreted as a tab. So remember, the easiest way to fix that, in my experience, is simply to escape those \. There we go. Note that this is not a problem when we're doing Mac OS or Linux directory paths. So we could do this all day long. Finally, just as a point of reminder, remember we can mix and match our double quotes all we want, as long as we're consistent. Now let's review some rules and best practices that govern the creation of variables, also called names in Python. The general syntax or form for Python names is either a letter or an underscore plus some programmer-defined length of letters or digits. All right, so the bottom line is you can prefix your variables with a single underscore. Underscore eggs would be a legal variable name, and we can use a letter. Notice that case is significant. A name called eggs with lowercase e is completely different from a name we define with e as uppercase. Notice also that besides this rule, how we can start names, the main body, or that is to say the remainder of the variable, can be letters or digits, but that's it. You can't use special characters like, say, the pound sign or the exclamation point, just alphanumerics. You also, this hopefully stands to reason, you cannot use any of the reserved words, that is to say the built-in Python statements, in your names. As we go along, we haven't seen any of these bad boys yet, but certainly in the Python literature and as we go along in the course, we're going to come across system-defined names. these are prepended and followed by 2 underscores, okay? Self would be an example of a system-defined name. Looks kind of weird when you first see these. We're going to discuss them in great detail later in the course, so that's all I'll say about them right now. A trick I'm about to show you in the next demo is that while you're in the interpreter in idle, you can just submit an underscore to repeat the last expression that you submitted to that interpreter. Finally, let's review again the importance of being precise in our terminology. Remember, a name is a variable, but the thing about it is with Python, a variable is defined a bit differently than from what it is, say, in other languages. I know I'm using C as the reference here. I think it's a good one, though. In C, a variable is a location in memory where you can store data of a predefined type. That is to say, we declare the variable, or we define it, and when we declare that variable, we bind it at declaration with a particular data type, whether it's an integer type or a string type, etc. And if you've used C, there's actually many different string types, many different integer types. It gets pretty complex. We can get spoiled in Python with it being as simple as it is. But with Python names, you actually never declare them separately. Think about what we've done in the previous handful of nuggets. Any sample code I've given you, we've defined a name and then immediately assigned it to a value. That takes a little getting used to folks who come to Python from other languages who are used to declaring a variable, associating it with a data type, and then initializing the variable or assigning it to a value. Speaking of the assignment process, on the left-hand side of this assignment, of course, is our name or our Python variable. On the right-hand side, officially the term here is object. It's an object that is associated or bound with a particular data type. You've also noticed that we've used a dot syntax for, let's say, strings, and we brought in what are called methods, which are, as we've discussed, nothing more than functions that can be applied to a specific name or data object. This syntax is important in most programming languages, and technically using the Python nomenclature, the second aspect here doesn't have to be just a method. Officially, you have your object name, dot, and then what's called an attribute. The wording gets a little bit fuzzy in Python compared to other languages. If you've done work in the .NET environment, for instance, there's a clear differentiation between, say, a method and a property. A property is generally some characteristic of an object, whereas a method is, as I've said, a function, something that does something. All this stuff is called attributes in Python, and we access attributes of an object by giving the name of the variable, dot, and then that attribute. So as we said, we don't just say, here's a name, and then here's its data type, like we would in, say, Java or C, etc. We create a name and then assign it to a value, and then it's typed dynamically depending upon what data object we've attached. Now, you know the rules with regard to mutability and immutability. What this means is, in this case, the name spam is bound to a data object that's of the integer type, and the value is 1. Now, what we could do is do this. And at first blush, you might think to yourself, wait a minute, I thought numbers in Python were non-changeable. Well, what's actually happening under the hood, and we're going to talk about this more in the next nugget, is that this old 1 object still exists in memory. We've simply taken the name and uncoupled it from the data object and pointed it at a new object in memory, you see? So this 1 actually is just floating in the ether, and a process in Python and in most programming languages nowadays called garbage collection. This process will run periodically and remove old data objects from memory that are no longer being referenced by names, you see? Now, you notice here I was able to create eggs in both ways, uppercase and lowercase. This demonstrates the significance of case. Remember, we can lead off a name with a single strike of the underscore. What do you think? Based on how this object looks with the parentheses, what type of object is this? This is a review question. Yep, it's a tuple. Now, how about this? You think this will work? Nope, syntax error, invalid syntax. Simple as that. Now let's take a look at comments and documentation strings. A comment in your code is simply information that you add to annotate your code for easier understanding and legibility. The way Python handles comments is anytime the interpreter comes across the pound sign, the hash mark, or formally, my favorite way to refer to this, the octothorpe, Python will ignore any information that comes after that hash mark for the rest of the current line. Okay? Now, hash mark comments, similar to how they work in Linux and Mac OS, is that they'll only allow you to comment on that line. And we don't want to be crazy about documentation. Some folks are absolutely vociferous about the importance of documenting your code. In my professional experience, I think a balanced approach is best, where yes, we're documenting code elements that are not obvious. I mean, we don't want to define a string and then pound, this is a string. That's just a waste of space, and that actually has the opposite effect of making our code more difficult to understand. Now, how we handle multi-line comments is in triple quoted string format. I just showed you how to create actual honest-to-goodness triple quoted strings that you use in your code, but you can also use these for multi-line comments. It just depends, again, there's overloading going on here. Depending upon where you're invoking or how you're invoking the triple quoted strings, this allows you to actually create a doc block or a documentation block. Many companies and software developers like at the head of their module files to have a documentation block that gives the author's name, the author's contact information, if you're publishing this code, maybe copyright data, etc. So as you see, comments have a couple good purposes. One, for team members to improve legibility, and number two, for legal footprinting purposes. Documentation strings are a really neat feature of Python that involves the triple quoted string. The bottom line is, if you add as the very first statement in your, let's say, function or a class or a method, or most commonly in a module, if you add the very first thing being your comment information, in particular a triple quoted string comment, then you can actually query that module, function, class, or method to retrieve the documentation string. Now, what you put in your doc string, as I said, it could be disclaimer information, the who, what, when, where, why, and how with regard to that code. But you can also fetch the documentation string by running a built-in attribute, _doc, _. We mentioned these just a few minutes ago, actually, these system reserved attributes, and I'll show you how to use the built-in dir and help functions to generate the documentation string data. To demonstrate comments and documentation strings, we're going to create a new Python script file by, in idle, opening the File menu and selecting New Window. In this new window, the first thing I'll do is save. And actually, let me bail out of here for just a moment and come back to idle, because in this demonstration, I'm going to create a module or a script file called wiper, and it's going to have that hack that I gave you earlier in the course for wiping the screen. I'm going to create a simple one-line function that prints 100 new lines. No big deal, it's essentially toy code. But the bottom line is, in order to import a module, the module has to be in the correct Python path. And what you can do in idle that's pretty cool is in the File menu, we can select Path Browser. And Path Browser gives us a dump of some of the information contained in sys.path. Sys is, in fact, one of the standard library modules in Python. And this gives us the default search path that Python itself used. We talked about Python path in the very beginning of this course. What I'm going to do in this example is I could store my new module in site packages, or I could just put it in lib on a Windows computer, C Python 31 lib. This is where the built-in modules and packages live by default. We're going to talk more about imports and modules specifically later, so just to give you a little bit of background, because what we're going to do is come back to our now untitled file, and when I save it, I want to make sure I'm putting it in one of those paths. I'm just going to put it in lib now. Call the file wiper.py, making sure to remember the extension. And note, the first thing I'm going to do in this module is create a triple quoted documentation string. Let's have a look at what I've done here. Between the triple quoted strings, I've added my metadata. Now I'm colorblind, so I have no idea what color the interpreter is using, IDLE is using for this formatting. But remember, we can go to Options, Configure IDLE, and come over to the highlighting page and customize how things like comments show up, which of course this is. I also, while we're here, want to show you on the Fonts Tabs page in IDLE Preferences that the default is set for 4-space white space indentation. And it tells us here explicitly that the Python standard is in fact 4 spaces. Good and good. After our documentation string at the top of this module file, we have our function, which we now know is not a simple but a compound statement that includes a header. The def keyword or the def statement gives us an indication and gives Python an indication that we're defining a function called W with no input parameters, and it simply does one thing. It prints 100 new lines, and we now know what a new line is too. Good deal. So let's save this file. I'm actually going to close it and come back to the Python shell, because what we can do now is import wiper. Notice if we didn't have the file, that script file stored in the Python path, we'd get an error here. I'm then going to run the dir function passing in wiper. Have to get the syntax correct, of course. What dir does is give you a run of all of the contents of a given object. In this case, I passed in a module, so it's giving us all of the internal attributes. These are the ones that are surrounded by double underscores. And then at the end of all of the internal attributes, any functions, classes, etc. that you've defined in that module show up. Here we have just the W. Now we're going to talk about online help in great detail in just a moment, but one neat way to use online help is to pass in, well, in this case, a module name into the function, and this comes back with the name of the file, the specific file path where the file is located, and then check this out, under description. It pulled my documentation string, didn't it? And then it finishes with a run of any functions contained in the file. Finally, I'll show you how to use one of those internal attributes. I'm going to print wiper dot. Remember what I told you, that we have this dot syntax where we can separate an object to a method or some general attribute. It gives us W in the list. That's the one that we created. But I'm now going to call under double underscore. As soon as I hit that, you notice that the list changes in idle. To get a documentation string, you arrow down, hit enter, and this doc attribute pulls back just the documentation string information. Let's finish with a flourish by actually running the function. You'll notice that when you're in an interpreted environment here, even though I've imported wiper, the Python interpreter never assumes. That's actually a core design principle in Python. We never want to take ambiguity and make an assumption based on that ambiguity. So in the interactive environment, we're going to need to fully qualify our W function by typing wiper, the module name, dot, and then its attribute, which is the W function. Our final topic in this nugget is that of online help. I often tell people, it's certainly what I've been taught by my mentors, and I pass it on to anybody who will listen, that being a successful programmer, IT professional, or just a successful person in life isn't all about what I know. What I know at any given point in time may grow stale. The bottom line is, do I know where and how to find the answers to the questions that I have? So that's my motivation in giving you this whiteboard. We're certainly not going to have all of the attributes of the standard library modules in our mind at any point in time. We'll have a handful of them, the ones we use most often. But how do we find and query information about this, given that we know what the standard library is, for instance, and we understand what modules are? Now, speaking of standard library, the online help in Python 3 is brought to us courtesy of a module. This module is called PyDoc, and it's really awesome. I'm a big fan of it. The PyDoc module includes several really useful functions. The one that we're going to focus on now is the help function that has a lot of different contexts. As we're going to see in the demo, you can run help with no arguments to go into an interactive help mode to query information about modules, statements, etc. Or as you saw in the previous demo, you can pass in a name and get help specific to that name, attribute, etc. To make things even more rich and robust, we have the PyDoc HTML viewer. You see in the lower left, that once you've done an installation of CPython, at least 3.1, the one I'm using, you'll notice that we can go to Start Programs, Python 3.1, and open Module Docs. And what this does is give us you know what this TK is, right? TK Enter, the graphical user interface toolkit that ships with CPython. It gives us PyDoc as a GUI, and it actually instantiates a micro web server that listens on some port on my system 7464 on the local host. You can do an interactive search for your modules for a particular attribute, or you can just open the browser and drill in that way. Let's go ahead and take a look at this. In the interpreter, why don't we first just run help with no arguments to go into the interactive online help utility. It tells us in the last paragraph here to get a list of available modules, keywords, or topics. You can type any of those words. Why don't I start with keywords, considering we were discussing Python keywords earlier in this nugget. Tells us friendly enough, here's a list of the Python keywords, enter any one to get more help on it. Which one do we want to look at? How about import? Now all of this is itself written in Python. Remember that PyDoc is in fact nothing other than an ordinary garden variety Python script file. And everything we're doing here, reading all of this really useful text, is nothing more than working from a user's perspective with a Python application. In fact, it's a good learning experience for you to crack open something like PyDoc and look and read those class and attribute declarations. You can quit out of the interactive help by using Q, and it takes us back. We know the triple chevrons is the ordinary Python interpreter prompt. Let's import a module. One of my favorites is the random number generator, random. You have to import that module into memory before we can start querying it. If we run first of all dir on random, that's going to give us a list of all of the built-in, the system-generated attributes, and then after that, the ones that we can actually use, the functions that are created in that module. One that I use a lot is randint to generate a random integer within a certain range. So speaking of which, if we want to know more about this, we can do random.randint, pass that into help, and it gives us our documentation string that's in that random module under the randint function, you see? If we open the Module Docs item from the Windows Start menu, it'll give us this TK Enter PyDoc application where we can, as I said earlier, perform a direct search into the standard library. We can quit serving, or we can open the browser. First, let's do a search. Let's say we were doing operating system specific calls in our Python program, maybe for systems administration and automation scripts, and we wanted to drill into the OS module in the Python standard library. Let me expand the window here. Now OS is actually giving us a lot of results back. So if I come down to the middle of the list, I can find the OS module. This is specifically what we're interested in. OS routines for Mac, NT, or POSIX, depending upon what version we're on. And then we can go to selected, or we can just open the browser to go to the index page. I'm going to go to selected here. And what you get is a nicely formatted web page that describes the module in question. Tells us this one is CPython31lib os.py, OS routines, etc. We already read that. Tells us that programs that rely upon this OS module stand a better chance of being portable between different paths. We have some related modules here. We can just click those to drill directly into them. These are nicely color-coded, by the way. These colored banners differentiate each portion of the file. We have a series of classes. Classes are essentially reusable objects that encapsulate a whole bunch of functionality. The module that I created earlier, the wiper, contained just a single function. On the other hand, if we're using object-oriented programming, OOP, instead of procedural, what we could do is create a module that consists of classes, and then each class in turn may have a whole lot of methods attached to it. And that's what you see here. You go through here, look at your classes, and then there's information on functions that are encapsulated in those methods. Next, we have actual raw standalone functions. And that takes it all the way down to the bottom of the page. Now, if I come back up to the top and click Index, this is the equivalent of just clicking the Open Browser button in the PyDoc web server interface. And note that we can query built-in modules, and then all of the paths in the Python path are shown up here, one after the other. There's our CPython31lib, and you can just click whichever one. There's random, actually, so let's give that a click. There's our classes, our reusable objects, in other words. And then we come down to the standalone functions. There's my favorite randint right there. And you should notice that this documentation string is what we saw in the interpreter when we ran the help function and passed in random.randint. Statements, documentation, and online help review. More than anything else, friends, I hope that now that you've studied this nugget, a lot of what we've learned to date in the previous handful of nuggets is starting to make some sense. Whenever I go and start a new endeavor and learn a new technology, at first it seems like I'm learning a whole bunch of separate, disparate things that bear little or no relation to one another. That seemingly is what we've done in the previous few nuggets. Now we're starting to wrap up and combine these base elements, and hopefully you're starting to develop a more comprehensive knowledge web. Certainly we're going to keep building on that through the remainder of the course. I hope you're as excited as I am. Formally in this nugget, we examined Python statements, the built-in keywords that form building blocks of your Python programs. We then looked at rules and best practices for naming variables. We looked at Python-specific nomenclature, that is to say that the name can be bound to different objects depending upon the immutability or mutability of the data type under consideration. It takes a little while to start to understand that. I hope you're clearer with that distinction. We'll keep revisiting as we go along. We then moved into commenting and documentation strings. You should be familiar now with how to use the pound sign to do a one-line comment, triple quoted strings to do multi-line comments, and these special attributes called docstrings. Finally, we looked at online help. It's not so much what you know as if you know where and how to look up the answer. I hope that this has been informative for you, and I'd like to thank you for viewing.